zoom out a little here. All right, this is an introduction to graph theory, and then we'll get to graph coloring. So what is a graph? You've probably been exposed to graphs a lot in maybe algebra or calculus, but that's not really the type of graph that we're talking about when we talk about graph theory. So for us, a graph is just an ordered pair consisting of a vertex set V and an edge set E. So these are each sets here, V and E. And so the vertex set is just a set of elements, right? Those things could be anything. And then in particular, the edge set needs to consist of two element subsets of V. So this seems like a pretty abstract definition. Let's try to think about what it really means. I'm going to give you an example here and say that the graph G is consisting of the vertex set V, which has elements A, B, C, D, and little e in it, and the edge set E, and that edge set needs to consist of two element subsets of the vertex set. It doesn't need to be all two element subsets, it just needs to be some of them. So for example, we have AB, we have AC, AD, BC, BE, and DE. Now, this is the way that we define a graph, but the way that we think about a graph most often is using a diagram. Okay, and so the vertex set is really just going to be points, right? Dots. So we've got point A, point B, C, D, and E. I drew them in a circle like this, but it really does not matter how you draw them. You can draw them however you like. And then the edge set is telling you a relationship between pairs of vertices. So for example, the fact that AB is an element of the edge set E means A and B are connected in some way. We're trying to express some sort of relationship between A and B. And so in our diagram, we can represent that using some sort of a line segment to connect them. It doesn't have to be a straight line, right? But just some sort of curve that's connecting points A to B, right? Because AB is in our edge set. Similarly, AC is in our edge set, which means A should be connected to C. AD is in our edge set, so A has to connect to D. BC is in our edge set, so B connects to C. B connects to E as well. And then finally, D connects to E. So in the end, we get a diagram that looks like this. Okay? Your diagram could look different if you drew your vertices, right? We call each one of these a vertex set. Plural, they would be vertices. If you drew your vertices in some other order, this graph might look a little bit different. But all you really need for a correct graph here is for all of your vertices to be there. So we have all 5 of our vertices here. And for there to be some sort of a line connecting each pair of vertices that show up in the edge set. Okay, so notice, for example, the set CD doesn't occur in the edge set, so we don't have a line connecting C to D. And similarly for A to E. So we don't need all of the two element subsets, we just need some of them, right? Now, the order of G is defined to be the number of vertices. In other words, the order should be the size of the vertex set, the cardinality of the vertex set. In this graph here, our number of vertices is 5. Okay? The size of G is defined to be the number of edges in your graph, the number of lines connecting, right? Connecting lines. So that's going to be the cardinality of the edge set. Well, it's sometimes a little bit harder to count it on the graph itself. You want to make sure you don't double count, but you've got 1, 2, 3, 4, 5, 6. It's easier to count it up here. This is 1 edge, 2, 3, 4, 5, and 6. So the size of this graph is 6. One more definition. We say that if UV, before I do that, writing out the edges like this using a whole bunch of curly brackets can be pretty tedious. And so oftentimes when we describe the edge set, instead of actually writing out this subset AB in curly brackets, we'll just write AB together. And you could write AB, or you could do it in the other order BA, because there's no order to a set. But this is just saying that there's an edge connecting A to B, and vice versa. Then we have AC, AD, BC, BE, or DE, right? This is just a shorthand way of describing the edge set. Okay, now with that in mind, if UV in general is an edge of a graph G, then we say that U is adjacent to V. So in our example above, we could say something like A is adjacent to B, because AB is an edge in our graph. There's a line connecting A to B, but C is not adjacent to D. All right, so maybe already you can see why this sort of an object in math can be useful. It's describing relationships between pairs of elements. And we'll see that we can use this to help us in the warm-up problems in the next video. But for now, I'll give you one example of how we can use graph theory in an application problem. Okay, so this is called a matching problem. So suppose that we have 4 employees and they need to complete 4 tasks. And we know that some of the employees can only complete certain tasks, not all possible tasks. So one question you might want to ask is it possible to assign one employee to each task? So I've drawn a graph to model this situation. So I have 4 employees, A, B, C, and D, and I have 4 tasks that need to be completed, E, F, G, and H. And I drew my graph in such a way that if there's an edge between an employee and a task, that means that employee is capable of doing that task, right? So employee A can complete task E or complete task F, but they don't know how to do tasks G and H, etc. So what would it look like to try to solve this problem using the graph? Okay, well, think about it for a sec. What we're trying to do is find a way to assign one task to one employee in such a way that all 4 employees get used and all 4 tasks get completed. Okay, well, let's try to think through what would need to happen here. Task F can only get completed by employee A. Nobody else knows how to do that task, which means when we do this, we're going to have to assign task F to employee A. All right, now employee A has already done their task. They're not going to be able to do anything else, so they won't be able to complete task E, for example. But that's okay, because employee B also knows how to do task E. So let's assign task E to employee B. All right, other issues here, employee C only knows how to do one single task, and that's task G, so we're gonna have to assign task G to employee C. And finally, we have 1 task and 1 employee left, and luckily, employee D knows how to do task H, so they'll get assigned here. Okay, so this is called a graph matching. We found a way to match up employees to tasks in a way that you can see, based on our highlighted edges here, this is a bijection, right? It's 1-to-1 and it's onto. Okay, now let's look at a similar problem, but with different employees and different tasks. Is this possible? Is it possible to get a matching here? Can we assign tasks to employees so that every employee does exactly 1 task? I mean, we could try, right? For example, L can only do task M, which means we would have to assign L to M. And K can only complete task O, so we would have to assign K to O. And well, now we have a problem because there's only 2 tasks left, and the only person who knows how to complete both of them are J. Right? The other issue is I only knows how to complete task O, but somebody else is already doing task O, right? So there's no way to actually complete these last 2 tasks using people I and J. So it's going to be not possible here. And this is a whole area of graph theory, the idea of using of graph matching to try and figure out if it's possible to assign vertices in one set to vertices in another set using the edges of the graph. Okay, but I claim that we can also use graph theory to help us address the types of problems that we were doing in the warm-up. Right, so I'm going to give you one more similar problem here. So suppose that a state is divided into counties, as in this map below, and the map maker wishes to color each county. But if any 2 counties share a border, we want to make sure that they don't have the same color. The question is it possible to do this? So I'm going to stop this video here, and we'll come back and try and answer this with graph theory in the next video.